to FinFET, right? This is the reading you can read, but we don't have much time, right? I'm not going to start with the all this lattice system or whatever, right? And we don't need that. We are not so deep, right? This class is more like a survey class, but still we want to understand that for crystal, they have, for in a crystal is anisotropy. What does it mean? Now, if you stand in your room, right? You go left, go right, go 90 degree, whatever, you basically feel the same amount of resistance because the air is kind of isotropic everywhere. But crystal, they are what? Regularly arranged atoms. So you can definitely feel it is different. Just like in a classroom, you have people sitting on rows, right? In certain direction, you can go through them easily, right? For example, if I have a 2D fake crystal like this, right? You realize that, hey, if I go through this direction, my resistance will be different if I go to this direction, right? That really depends on the how much interaction I have with the atoms, right? So this is anisotropic, right? So that's why we need to know the direction of the crystal, right? So we have X, Y, Z, the coordinates first, right? Start with the coordinates, and what do we call, right? We say, we draw the plane, right? For example, this plane is going in this direction. We call it 1, 0, 0. So how do we call this? We basically draw the plane and see how it cuts. Here it cut at 1, right? Where does it cut at? Where does it cut at Y and Z? Do you know? For X, Y, Z, right? It cut at 1, right? This plane. Where does it cut at Y? Can someone tell me what is the intercept between this plane and Y axis? Can you trace it and tell me where it cut? Does it cut at 0? Does it cut at 1? Cut at 2, 3, 4, 5, negative 6, 1,000, 100?
1.
Where?
1.
1. But I don't see this plane cut at 1. I'm talking about this plane. It cut X at 1.
0, 1, 0, 0.
You think it cut at 0, but I don't see that it's cutting at 0 because Y equal to 0 is here.
Yeah, no cutting.
No cutting. What is the meaning of no cutting?
It's parallel or
parallel. So have you learned that if I have two parallel lines, where do they meet?
infinity.
Infinity. Right? No cutting. You're right. It means that they cut at infinity. So same for Z, right? So then we get the so-called Mueller index, right? A very simple review. It's just 1 over 1 over infinity, 1 over infinity. So it is 1, 0, 0. So this is the phase of the direction of this phase, right? As another example, right? This one cut at 1 for X, right? You see it cut here. It cut Y at 1, but again for Z, it's parallel. It cut at infinity. So the Mueller index is 1 over 1 over 1 over 1, 1 over infinity. So it is 1, 1, 0 plane, right? How about this last one? Where does it cut at X? Someone tell me. Where does it cut at X for this shaded plane? This one's supposed to be easier than the first one. Where does it cut at X?
Or all of them?
Huh?
It cuts all
Say
of them?
again.
1.
1 for all of them. Exactly. Then 1 over 1, 1 over 1, 1 over 1 still give you 1, 1, 1. Okay, so this is the 1, 1, 1 direction, right? So you always will see people talk about silicon. They are, okay, this silicon is 1, 0, 0 direction. This what this silicon mean? I mean, this wafer, right? Your silicon is a 3D lattice. Of course, this is not the real one, right? This is a bad drawing. Like this is a 3D lattice, right? So you give me a wafer, right? Wafer is just like a pancake. So I want to know, what is this direction going up? What is this direction going outside of the screen when you give me this pancake? Well, it can be this direction if I cut it here. It can be this direction, or it can be any direction, right? That's why I want to know. Why? Because it's going to affect my transistor's property. Okay, so that is one thing, right? So this is crystal orientation. Now, another thing is, we don't have time to do this. I assume you know. If you don't know, that's fine. The point is, as I told you last time, a carrier in the crystal, they have different mass. We call it effective mass. Usually we give a star in different direction, right? Last time I told you about the effective mass or effective force. Remember, I say you try to push a guy, and if you cannot see anything, you just try to feel how the guy responds to you. Then you just try to judge whether the guy is heavy or not, right? But you can have a very nice guy, right? Very nice way, maybe a baby in front of you, but someone behind the baby was holding the baby, right? Or many people. You push it, then what happened? You feel that it's not moving. You thought, wow, this must be a big guy, because you cannot see. Or in extreme case, when you push it, you provoke the mother who's holding him. She actually try to push the baby to you. Then you feel, wow, this baby has negative mass because I push it in that direction. It traveled to the opposite direction. So it has a negative mass. So this is the same in crystal. In crystal, you have a lot of electrons. The electrons traveling, and you have lattice. They are in the order. So overall, when you solve all the Schrodinger equation, all the kinetics, you turn out that you can describe them as if they are in the free space, but with a special effective mass. So here, try to tell you that you have two different mass. For example, we have 6 valley. 6 valley, last time I mentioned, are the lowest energy that you can have, the valley in the energy. If the electron is here, if we're going to this direction, it is called the longitudinal mass. It's about 0.19, I think. Yeah, 19. No, sorry, this is not the longitudinal. This is the, maybe I have a label problem. This is longitudinal, but this is a heavy one, 0.91 electron mass. Okay, so very close to the electron mass. M0 means the electron at rest in the vacuum, right? But in this direction, you see the curvature is smaller. It actually has smaller effective mass, 0.19, okay, electron mass. So it is much lighter. It's how much? Almost 5 times, 4.5 times lighter. What is the meaning? It means if you apply electric field, it travels faster in that direction. Okay, so from the basic physics, we know the mobility is actually equal to Q times tau divided by the effective mass. What is tau? Tau is just the mean free time, right? The time between which you get scattered, right? You will get knocked by someone else. So it's just like, again, in the, let's say, an army array of people who line up, you try to run into there, right? Sometimes you don't run well, you hit a guy, or maybe they keep vibrating. That is what happened to the lattice, right? When suddenly, when you're running well, some people will just vibrate to your direction and hit you, then you slow down. And you keep going, hit you again, you slow down, right? So the time between these two hits is called mean free time. So if it is longer, it means I have higher mobility. At the same time, if my effective mass is larger, it also means that I have higher mobility, lower mobility, okay? So why I want to introduce this, I don't need you to have very deep understanding on this, but I want you to appreciate, to know that you need to know that crystal has different orientation. And because have different orientation, you actually have different electrical property. One of them is the effective mass. Your mass is different when you travel in different direction. In certain direction, you are heavier. The electron is heavier. In some direction, it's lighter. And the mobility is related to the mass inversely. Is that clear? Any questions?
So is it more difficult for the electron to move through the crystal face?
More difficult for electron to move in where?
Through the plane that you're showing there?
Through the plane, then it depends. Oh, it is more difficult to move in this direction, but this direction is easier. Okay? Make sense?
Yeah, thank you.
But however, now the point is this. You see that I have 6 valley. For the electron in this valley, it is easier to move in this direction. So due to symmetry for silicon, right, overall, they are the same. They are isotropic because I have 6 valley contributing to the overall effective mass. Okay, but we are going to do something, then they will be different. Now here's trying to show the electron mobility, right? So here try to say first, we do have this one means here trying to say the mobility. So what does it mean? This is the phase, okay, of your wafer, or of the phase of the channel. Okay, so what does it mean? For example, if you may have a transistor like this, right? So this is the transistor that you have, N plus, right? I'm drawing a 3D diagram. Now, your electron is moving in this direction, right? This direction is talking about 110. It means this direction is 110. It means this direction, okay? You're trying to move perpendicular to this phase, okay? But this is not enough. How about we also need to know what is the surface orientation? This one is 100, right? This phase on the top is 100, and that electron is moving in 110. You see that I can have 100 phase, but then the electron, if I change the transistor orientation, it can move into the screen. It can move 45 degrees away from the screen, right? So that's why you can have the same. Here, let's compare it. You can have the same phase, 110 phase means this is 110, but you transport in different direction. Okay, then you see it is dependent on not just the surface, but also the orientation. Okay, and same for the hole. They are dependent on the orientation. This is the most important thing I want you to take home. Okay, if you cut the, if you make the transistor, depends on what type of wafer and depends on how you lay out your transistor. You have different mobility. It means you have different current. So, okay, any questions?
I have a question, Professor.
Yeah.
These orientations, are these random orientations, or do we have any control over this orientation on the wafer that you mentioned?
It depends how you cut the wafer. First of all, for this phase, right? Remember, we have, this is a 3D silicon. If you cut it differently, then your phase is at different orientation, right?
Oh.
Right? So this is what you can control. And then on top of this face, you draw your transistor. You can rotate it, right? So this is also what you can control. But you cannot choose arbitrary face, right? Because once you cut this wafer, it then on the surface, you don't get all the possible orientation. Okay, so this is just the limit. But in reality, the vendor is only going to give you 3 types, usually 100, 110, and 111 when you buy the wafer. And then you lay out on top of it. And usually what we use is 100 or 111. Actually, also 110. Actually, I have not done experiment for almost 20 years, so I don't know details. So, but at that time, it's usually 100 and 110, and also 111. Okay, do I answer your question?
Yes.
Okay, good.
Is the orientation of the silicon usually designed or like fixed?
Yeah. So usually when they make the silicon wafer, they cut in the 100, 110, and 111 direction. They try not to cut in some arbitrary orientation because the demand for these are the highest. Let's look at this. This is what a wafer, right? Just an example. First of all, actually, I don't know what orientation it is. I think this is 100. First of all, you cut in 100. Do you see this? If you have this silicon, I cut in this direction. I just cut this plane, right? Then I get this wafer. Okay. And usually it has a notch just to tell you, okay, in this direction is 110. Then what does it mean? Then it means this is also 110, 100, and 100. So this is 45 degrees. Now you may feel confused now. Why you call this 100, you don't call it 1010 because it's Y. You're right. But in terms of electrical property, they are the same. So we don't have to distinguish. So if you now you can call this 001, doesn't matter, right? They are the same. Okay, so now can you see that in this wafer, top is 100, 45 degrees is also 100, and the middle one is 110. Okay, but now we're talking about FinFET, right? Then you grow the FinFET, you see that this is 100, the face, this is the face, right? And exactly is, you see I put 100, in this direction, it is 100. Okay, and then you can rotate it to perpendicular to this one, then you get 110, right? So when you design the FinFET, it's more complicated because now you have 3D and you can rotate them, right? But you don't want to rotate them arbitrarily because this increases your layout area. You are going to have a lot of irregularity. Okay, so are you okay with this picture? Everything clear? Do you know what it is about?
Can you explain a bit more why the 100 is the same as 010?
Yeah, 100 is just talking about, let's say if I call it 100, maybe you say the cut X at 1, right? 010 means cut Y at 1. But what is X, Y, Z? It doesn't matter to me. They have the same property, right? Let's look at this one. If you go in this direction, let's say I have a crystal, you go in this direction. Can you distinguish this direction and this direction? If you are electron walking in this infinite array of atoms, going in this direction and this direction, do you think they are different?
No.
No, right? Because the environment is the same, it's infinite. I just keep going. I see after every A distance of A, I see one atom. After, right? It's just a repeat. So yeah, you can call this 010 in this system, but it's the same in terms of the material property. That's why we just call it 100. But when we, yeah, but if you like, you can put them differently. Do I answer your question?
Yes, thanks.
Right, so this is just an example. Now, so let's do a little bit more about FinFET, right, to understand their calculation. Hold on. So this is an example of FinFET. So how do they do FinFET? We have been talking about only one fin, right? Like this. But this is our fin. Right? We have been seeing the fin. And then we say, okay, I have a big structure here. Let me don't draw it. I can never draw it well. Source string, right? And then we have a gate. This is a FinFET. Is that okay, everyone, about what I'm drawing, a FinFET? But in reality, what we will do, we actually won't rely on one fin. So this is S, this is D, and this is the fin without the gate. Okay, this is the fin. And we have many fin. Now, if you do a cut in this direction, right, A cut, A cut, then what does it mean? I'm doing this. And this is A dash, okay? So then you get this A dash. Is that okay? So you have many fin next to each other. So between the fin here, no current, right? Because you don't have transistor there. You only rely the fin 1, 2, 3, 4 to conduct because your source string is into the screen, right? So here shows a typical, just let's say this is a bulk MOSFET, right? And then this is the fin, right? So what I'm drawing here, do you see this is the pitch? Here is where you conduct the current. So this is A, this is A dash. The current is going from here. Okay. WSI. So you see that the pitch is important. You want to make the pitch very small. And you also want to make the WSI very wide and make the TSI very high. But that will make the process very difficult. But however, this is your goal, okay? First of all, any question about this picture? So in this class, we need to learn how to see many pictures because a lot of 3D stuff, right? Any question, anything that is not clear? Right, this is source, this is string, right? Source, string. Anyone has any questions? So you won't memorize in one day, right? You need to keep revisiting to make it something internalized, right? And then you can say it very well before the interview.
I had a question. If you
Yeah.
apply voltage to that gate, does it open all of the sources to the drain?
You mean if you apply the voltage to the gate, right, it's going to turn on all the fin. This is the gate. So originally, the current cannot go through. You apply high voltage, you turn them on all at the same time. Just like this is about source and drain. If you have a negative gate, this is cut off, right? We're looking from the top. Okay, this is the bird view. Okay, if I look from the top view, right? So just like a bulb, you start from the top, right? And then it is off, right? And then now you turn it on, apply a gate bias, then your current can go on. Same for here. When you have a gate that is negative bias, all these fins are turned off, no electron. So current cannot go through. You apply a high gate bias, then the channel are formed inside this fin, then they can go through. Do I answer your question?
So is it not possible to have just one source and drain channel?
Oh, I see what you mean. Are you saying that why we need to merge the source string together for many fin?
Right.
Yeah, that is just for process issue. One is easier to do it. Second is that it provides less resistance because you can think about just like the water channel. They come here, then they can just fill everywhere easily and go to the contact. So usually we merge the source together and drain together, right? If you try to say, hey, can I have many separate fins? Yes, you can, but then you have to consider how to cut them. Then you actually need to cut them means you actually increase the layout area, right? It's just like you're playing the Play-Doh, right? You have the clay. If two things are very close, it's very easy to make them merge. But you say, oh, I want to make a space between these two clay, then you need to have very good art, very good skill to separate them. Is that your question?
Yes, thank you.
Okay, great. Yeah, good question, right? And why we want to do that, you will say we are wasting area. Yeah, but we do need so much fin to have a high current. But later you will find that maybe we just need one fin. Then you do need to separate. Okay. So let's do a toy model just to learn about how to calculate the current of the FinFET. This is a good intuition way. It doesn't mean that it is useful actually, right? Because we are going to use TCAD if you really go to there, but it tell you what's going on. Let's try to understand the planar one, right? What is the current for the planar one, right? I equals to, right? I can say maybe I equals to W times a constant. Okay, this is just a constant. K is just a constant. Okay, and we are just trying to say if you increase the width, my currents will go up. Right? You have many equations, but we don't need to go into the details of the equation. Right? So this is, let me call IDD. Okay. Okay. So you say that. Sorry, actually not just I missed one, and also the mobility. Right? The mobility at the top surface. Right? Remember, this is a bird wheel. Now the electrons are traveling here, right? So it is like this. You have this, right? Your electron is traveling here. This is your electron, right? So this is the top surface, right? This is the top, right? The mobility. How about for FinFET on the same wafer? It is this. No, it is not this. Right, this source string. So you do have some electron traveling on this top surface, right? But at the same time, you have some electron traveling on the side, right? Because the gate wrap you around, right? So from here, I say, okay, what is K? K is just equal to IDD divided by W mu top. Okay, just a constant. Now let me calculate the current in the FinFET. Let me put here so I have more space. What is that? Right, the first of all, these are the fin, right? So first of all, I have the top surface electron. Let's look at one fin first. Top first surface electron times K, of course, we have this K, right? And then times the width. What is the width now? It's WSI. So I'm just talking about what is the current traveling on this top surface of this fin, meaning here, right? It's mu top, right? K WSI. Correct? Then I also have two sides. This is the side, right? The two sides, I have mu psi, right? The mobility is mu psi. And then times K, right? Again, K. But then how wide is that? It's actually equals to the thickness of the silicon, TSI, right? This is TSI, how thick the silicon is. Right, this is for one fin. Right, this is one fin. Right, but then I have many fin. How many fin do I have? It is about equal to the total area divided by the pitch. Right, so if my pitch is 1, my W here is 10, then I can put 10 fin, right? And so this is the total current that I have. And now I can do some some simplification. Because I already found out what is K, right? I just put in K. So I know K equals to, let me take out the K. Mu top WSI plus 2 mu psi TSI W on P, then times K IDD divided by W mu top. W and then divided by IDD mu top. Is this okay? So this is just math. And then now I take out the ID here, right? Because I want to compare this to planar. How much increase in current do I have? Okay. And I multiply everything inside, right? So first this W got canceled. I have 2W. And then the P goes in. First, the mu top got canceled is WSI divided by P. And then plus 2 mu psi TSI divided by P times mu top. Okay, so you can see that, of course, it's as expected if mu psi increase, right? Or TSI increase, or the pitch decrease, or WSI increase, is going to increase my current. Right. Yeah, I may be going a little bit fast, not very clear. You can do it by yourself. This is just a simple math. But the main point to show you here is that if you can understand this, it means you really understand what I'm talking about. What is FinFET? Why I have top, why I have side. I want you to understand all this orientation. Okay, but only when you can write this and derive this, would you know what FinFET is about, what is the orientation, how they conduct the current. Although these are basically useless in real application. Any question here?
So those ones for the like a tri-gate FinFET?
Yeah, this is actually tri-gate. You're right. You can claim that, oh, you should not call it FinFET, just call it tri-gate. But not really important to distinguish. Yeah, because we're actually considering 3 terminal. And if it is real FinFET, then we don't have this term. You're right. This one will be gone. Okay. Other questions? Okay, please do think about that, right? Try to derive. Once you can understand, then I think you know what FinFET is. Okay. Now, so why we talk about all this? So we have done, we know what is FinFET, but FinFET is useless if you would just stop here. The main point is we are going to apply stress and strain to the FinFET to increase the mobility, right? We just say that what is mobility, right? Remember, mobility is about this. You apply electric field, you get the velocity, right? And this slope is the mobility. It tells you how fast the electron is going to travel faster when you increase the electric field. It depends on two things I just told you, right? One is the scattering time, one is the effective mass. So how can we increase the mobility? You almost cannot do anything. Why? Because they're just material property, right? Change material. Well, silicon is not good enough, too heavy, tau is too small, m is too large, then change it. They do change it. That's why you heard about people using gallium arsenide for the RF application because the effective mass is 0.067. Silicon is 0.19 in one direction, but on average, it's like more than that, right? 0.069, 10 times smaller effective mass. You can imagine how fast it can move. That's why people use gallium arsenide for RF application. Well, but gallium arsenide is not a good material for integration. We know silicon very well. The whole industry devoted 70 years or whatever just to develop silicon. No one can challenge it. It's just like monopoly. Okay, like AT&T in the past. The whole country, everyone use AT&T. They have all the infrastructure, right? But in US, you can just disband them, separate them into smaller company by law. But what's the point? You cannot do this to silicon, right? There's no monopoly law for silicon because they just do very well, right? So how can you change the tau and the effective mass? So that's why we come with string engineering, okay? Because after all, it is just about the lattice constant. You change the lattice constant, then you are able to do something, okay? So you squeeze it or pull it, then you have different mobility and different effective mass, okay? So here, I just want to quickly introduce you. I think you know already, but we need to make it clear, right? What is stress, what is strain? If you have a unit area, you apply a force. The stress is F divided by A, okay? Usually it is in Pascal or Newton per meter square. Okay, you stress something, what happened? It has strain. What is the meaning of strain? In 1D is this. This is what is original atom. Okay, now I apply a force to it. What will happen? Well, you know you're going to squeeze them. It might be something like this. Right? So the length will change from L to L dash. It was L. And it become L dash. So the strain is what? L minus L dash d. Actually, I should be specific. Should be L dash minus L divided by L. Usually is in percentage. Is this clear? Strain and stress. Okay. This one If it's larger than 0, we call it, no, actually, depends on, I mean, this one, if you, because the area vector goes up, right? But I don't want to do this because I don't want to go to area vector, but you know very well what is compressive and tensile stress, right? But for string, if it's less than 0, it is compressive, correct? Because you make L dash smaller. If it's larger than 0, it's tensile. Right? I want you to memorize this. You pull it and you compress it. Okay, so we have compressive and tensile. And there are two types, many more types, but two types that are more important in this class is uniaxial and biaxial. What does it mean? Uniaxial, it means that like this. You just pull it in two directions. This is a uniaxial stress. Can someone tell me, is this a tensile or compressive stress?
Tensile.
Thank you. Uniaxial, tensile. Because you're pulling them. Or you can pull it in all directions. This is called biaxial tensile. Right? You can also have volume, right? So this is something I think you know already, but we need to clarify because the sign is important, right? And later it's very important when we do the gallium arsenide, gallium nitride HAM. We're going to deal with this a lot. But so this concept cannot be messed up. Any questions? I feel that I might not have time to go to TCAT. Maybe I will just record in video. Okay. It's better to explain this clearly. So what do we do? It turns out that electron benefit from tensile stress in the transport direction and compressive stress in the vertical direction. Hole benefit from compressive stress in the transport direction. This is not FinFET. This is just a planar CMOS. So in the 2000 something, right? 2006 or 45 nanometer, 65 nanometer before 2010. This is a trick the industry use a lot to enhance the performance of their transistor. So what do? They, after they fabricate the transistor, they deposit a layer of nitride film. They just deposit, which has tensile stress. So what does it mean? It means the nitride is when they deposit, they feel being pulled away, right? So originally, the atom, let's say this is the equilibrium position. Right? But now, this is equilibrium, but now, this is the current atomic position. Okay? So you deposit a film like this. What does it want to do? Well, I'm under stress. I'm not going to yield, right? I'm going to rebel. I want to press them, try to restore to the original position, correct? So if I try to restore to the original position, I have a force. Try to push this up to here. Yeah, other sides also here, we also put to here, but let's ignore this one. We don't care because just have a force pushing to here on the silicon. Similarly, this side, I also has a force try to pull to here. So as a result, what happened to our channel? Is it being pulled away or being pushed, compressed? Right? Imagine you are human here, right? Someone pulling you here, another one pulling you here. you have a tensile stress. And because of this, electron go faster because it reduced the effective mass, it reduced the scattering that increased the relaxation time, mean free path, mean free time. And similar here is different because this layer is covering everywhere, so it tried to compress the gate. So it has some compressive force, right? This is just a zero order explanation. You really need to solve all the stress strain equation, right? The mechanical equation. Then you will see distribution of the stress and strain, right? It's not completely tensile in certain location, but overall, you will feel that this is tensile in this direction. And this is compressive in this direction. And this is called nitride stressor. This is very useful to enhance the transistor performance. Any questions? This is the old time, right? But how about for FinFET? For FinFET, you see here, we have X, Y, Z. Now, this is the stress, right? Again, what is the unit of stress? Anyone remember?
Pascal?
Pascal. Force divided by area. Just remember force divided by area, right? So they try to do experiment, and then they try to have a theory to predict what stress they have. From the stress, they can predict what mobility is going to improve, right? So for this particular structure, FinFET, this is source, this is drain, right? This is the gate. So electron travel in this direction, right? And you're talking about in the XX direction means the transport direction. We have 290. It means you're pulling them away, right? You're pulling them away. So this is I, right? So this is 290 megapascal. Okay. And then in the Y direction, you also try to pull them away. But in the Z direction, you try to compress them. And then you see that for different crystal orientation, you have different enhancement or degradation in the mobility. You don't need to memorize what happened, right? But I want you to be able to read paper, or some people tell you. Many of you will be a circuit designer in the future. I think not many of you are interested completely in to work as a device engineer, right? But the device engineer is going to tell you this, and you're going to request them to process, say, hey, my circuit is not good enough. Can you improve by 20%? And then they come back, say, hey, I already using 290 megapascal, no more. If I add more stress, it's going to crack, and then the U is going to reduce. Many circuit is not going to work, right? So these are the trade-off. Any questions?
So what does this stress do to? Is it the thing that?
Yeah. Now I'm going to explain, right? Last time we say in regular bulk transistor, we use the stressor. But for FinFET, you cannot just use stressor because it's 3D, right? Not effective, right? So the first thing what we can do is to use the source strain, right? So you see that this is silicon. Instead of source strain silicon, we have silicon germanium. Germanium is a larger atom than the silicon. This is called the atomic or the lattice constant. Okay, because they're more bulky, they need more space, right? But now you put it in silicon, what will happen? Okay, these are all kindergartner size. Now you try to fit all the adult in between, but you force them to have the same number. What will happen? Well, the kindergarten feel very relaxed because they are small size, but the adult is going to feel the compressive stress. Well, yes, they got compressive, right? This is the germanium, but they're going to react. They're going to push this kindergartner, right? Because they just stand next to the kindergartner. I don't want to feel so bad. Then don't feel so uncomfortable. Then I move a little bit to the kindergartner. I push the kindergartner and compress them. That's how you get a compressive stress, right? But we don't put purely germanium because of the fabrication issues and also other heterostructure, many issues, right? Usually we put a certain percentage. So for example, here we say what? Alpha, we will say silicon 1 minus Y, germanium Y. What does it mean? You will see the number can be 0. When it is 0, then it becomes pure silicon. When Y equal to 1, it becomes pure germanium. Okay? For example, if you have Y equal to 0.3, then you have silicon 0.7, germanium 0.3. That means 10 atoms, among 10 atoms, 7 are silicon, 7 are germanium. This is called alloy. I think you know that already. In chemistry or other, you study alloy, right? You mix the, you put the lead into the maybe steels, and then you change the property a lot. Here, we actually change a lot. We just don't put a small percentage, it's 30%. And with this, then you press it. Then you get compressive stress. Is this clear? Any questions? Okay, there's a way for you to do the compressive stress. I still have not answered your question. Now, how about for TCAT? So I think I mentioned last time already. What we do is at the source and drain, not TCAT, sorry. I mean, how about for FinFET, right? In the source and drain, we can put, for example, here, 50% germanium. So how do we write the composition? Si 0.5, germanium 0.5. And then you have compressive stress. Let's look at this. So I know vertical is the X, right, in the system. It is not drawn here, but now you can see that in the L direction, L, it means the channel length direction, you get a huge stress. This is in megapascal, so this is like negative 2.5 gigapascal. Okay, it might break something. Okay, so we do this, and then you look at the fin. This is a fin cut, right? And now you see that also this one has a very huge stress. I believe this is Z, this is X, this is Y. So you see that in the Z direction, I have a lot of huge stress, negative stress, compressive. And this will enhance the performance of the transistor, right? So we don't use stressor. We use the raised source string with higher mode fashion. Is that okay? Maybe I should set this ZC with this X. This should be XX, and this is YY.
So is that for NMOS, the FinFET? Because I remember for
This is for PMOS.
oh right,
PMOS, we
PMOS.
want it to be compressive.
Okay.
Right. For NMOS, we want it to be tensile. So what did we do? We use silicon carbide, not silicon carbide, carbon, right? This is very small. Maybe silicon, I don't know, 0.95, carbon 0.05. Okay. And then you get this tensile stress because it's positive in the channel to enhance the electron mobility. Make sense? Okay, so how do we fabricate string SOI? Now, this is another topic. Just can we start with a string layer, right? Instead of relying on the stress. So this is what we do. Right? We start with silicon, and then we increase the germanium fraction. So then they will still be relaxed. It means they are at equilibrium position, right? So this one has smaller lattice constant. And then we gradually add them, then gradually it relaxes. And then on top of it, we put silicon because they're bulky, right? They are very bulky. So the silicon are under what type of stress? Compressive or tensile stress? Think about this. I have some big germanium, right? And then I put silicon to align with them. So is the silicon under tensile or compressive stress? Silicon is supposed to be smaller than germanium. Now they have the same distance. So it is compressive or tensile?
Is it tensile?
Tensile, right? So they will be in tensile, right? Because they're being pulled away. Okay. And then we flip it. We do this hydrogen layer again, right? Remember, we first bond it. Okay. And then we by this wafer bonding, like what we taught last time, and then you get this string silicon on the oxide. So this is SOI. This is box. Then you can use it to make the SOI wafer. Okay. So I only have the last page, so I will stop here, but I think we are done, right? So I will record the answer in the video. So assume everyone is okay for me to share your assignment. I will try to hide your name, right? If you don't, please let me know if you don't want to, okay? Okay, so that's all I have. Feel free to leave if you don't have more questions. The only thing I want you to pay attention is that, you know, VTH, we talk about different things, right? What determines the VTH? One is the phi ms. Can someone tell me what is phi ms again?
The metal semiconductor work function.
Metal to semiconductor
Work function.
work function.
Difference, right? So metal work function is going to affect it. Well, in the bulk, we usually just take it for granted because we use P plus or N plus gate. They are not metal, but the gate work function, right? Maybe if you don't know, maybe I should better write it here. This is the silicon, right? And this is conduction band. This is valence band, right? From here to the vacuum is about 4.05 EV. Okay. And then, of course, from here to here is about 5.17 EV, right? Because the gap is 1.12 EV. Okay. So if I have an N plus gate, right? The Fermi level here. So what is the work function? Where's the work function when I have N plus gate?
Four,
Say again.
is it 4 EV?
Thank you. 4.05 EV, right? That's with a low work function gate. Okay. What if I have a P plus gate? What will be the work function? What's the work function? Based on the diagram I gave you. Work function,
5.17.
thank you. Work function is from Fermi level to vacuum, right? So from here, you see it's 1.57, right? So in the past, we only have N plus and P plus gate by using polysilicon. So we only have two work functions, 4.05 and 5.17. A low work function and high work function. No problem. Look at this. This is what I just said, right? This is the work function for N plus poly. This is the work function for P plus poly, right? About 4 and 5 and 5, right? So that is okay. But when we go to the FinFET, something changed because when we were in the bulk era, we have a big depletion capacity, depletion layer charge, right? That contribute to the threshold voltage. But now QD is almost zero in FinFET because usually we don't dope it, it's undoped. Okay, there's no heavily doped. Remember in SOI, we also make it lightly doped because we don't need it now. Okay, so as a result, the work function, I mean the threshold voltage actually is dominated by the FinFET. Sorry, dominated by the metal work function. Because of this, we cannot rely on N+ and P+. We need something what we call mid-gap level metal. So their work function will be close to the 4.5 EV at the midpoint of the silicon band gap. Okay, this is one thing. What's so special, right? So yeah, nowadays we keep saying that we use metal gates. The benefit is it has smaller resistance, right? You have less delay. Great. But actually, we are forced to do it at the beginning. Kind of forced to do that because we need to find some work function that is between the N+ and P+ poly to have the correct VTH. And turn out that if you have different metal have different work function. So actually, you find some mid-gap level work function that will fulfill the process. Is that okay? And here I want to just maybe I did not say it clearly in the past, right? The depletion layer, why we try to reduce the doping in the channel. Do you remember? Actually, I mentioned about that during the scaling process. I say when you scale the bulk transistor, you run into a lot of problem because it requires you to increase the substrate doping, increase QD, right? So now in FinFET, we just remove it. Why is going to help? What are the benefits? Do you remember? What's the problem when you have high doping for bulk? Maybe you don't remember. If you even you study, maybe you don't remember because there are too many things, right? That's why you need this, I call it immersion type of education, right? That we keep repeating. That's because remember, one is that mobility, right? If you have too much doping, you have impurity scattering. The mobility is going to degrade. So if I remove the doping, I increase the mobility, right? I can also increase make the subthresholds look better, right? I also reduce band-to-band tunneling. But most importantly is reduce the VTH variation. VTH variation. Okay. So I hope you can link to those. If not, go back to take a look. Okay. Any questions about this?
Sorry, Professor, that's because of increased doping?
No, because why need QD equal to 0?
Okay.
Yeah. Okay, so this is the last part of the FinFET. Now let me talk about quantum confinement again. I did not